So today I'm reading Reformer, the Efficient Transformer paper. It's from Google Research. Abstract. Large transformer models routinely achieve state-of-the-art results on a number of tasks, but training these models can be prohibitively costly, especially on long sequences. We introduced two techniques to improve the efficiency of transformers. For one, we replaced the dot product attention by one that uses locality-sensitive hashing, changing its complexity from L squared to LlogL, where L is length of the sequence. Furthermore, we use reversible residual layers instead of the standard residuals, which allow storing activations only once in the training process instead of n times, when n is the number of layers. The resulting model, the reformer, performs on par with transformer models while being more memory efficient and much faster on longer sequences. Introduction. The transformer architecture version 2017 is widely used in the natural language processing and yields state-of-the-art results on a number of tasks. To obtain these results, researchers have resorted to training even larger transformer models. The number of parameters exceeds 0.5 billion per layer in the largest configuration reported in 2018, where the number of layers go up to 64. In 2018, transformer models are also used in increasingly long sequences. Up to 11,000 tokens of text in a single example we processed in 2018, and when the processing other modalities like music and images, even longer sequences are commonplace. These large-scale long sequence models yield great results, but strain resources to the point where some argue that this trend is breaking NLP research. Many large transformer models can only realistically be trained in large industrial laboratories, such models trained with the model parallelism cannot even be fine-tuned on a single GPU, as their memory requirements demand a multi-accelerator hardware setup, even for a single training step. Do large transformer models fundamentally require such huge resources, or are they simply inefficient? Consider following calculation. 0.5 billion parameters used in the largest reported transformer layer accounts for 2 GB of memory. Activations for 64K tokens with embedding size of 1024 and batch size of 8 account for 64K times 1K times 8 is 0.5 billion floats, requiring another 2 GB of memory. If our memory was only per layer, then we should fairly easily fit a large transformer even on the sequences of length 64K or on a single accelerator. Furthermore, the whole corpus trained on BERT only requires 17 GB to store. Why is it then that we cannot even fine-tune these models on a single machine? Above estimation includes only per layer memory and input activation cost, and does not take into account the following major sources of memory used in transformer. Memory in a model with n layers is n times larger than in single layer model due to the fact that the activations need to be stored for backpropagation. Since the depth of the FF of the intermediate feed-forward layers is much larger than the depth of the model of attention activation, it accounts for a large fraction of the memory used. Attention on sequences of length L is L squared complexity in both computational memory and computation and memory complexity. So even for a single sequence of 64K tokens can exhaust accelerator memory. We introduce Reformer, which solves following problems with following techniques. They use reversible layers, splitting activations, and approximate attention computation. Reversible layers, first introduced in 2017, enable storing a single copy of activations in the whole model, so the n factor disappears. Splitting activations inside feed-forward layers and processing them in chunks removes the DFF factor and saves the memory inside feed-forward layers. Approximate attention computation based on locality-sensitive hashing replaces the complexity L squared factor in attention layers with LlogL, and so allows operating on longer sequences. We studied these techniques and showed that they have negligible impact on training process compared to the standard transformer. Splitting activations in fact only affect the implementation. It is numerically identical to the layers used in the transformer. Applying the reversible residuals instead of the standard ones does change the model, but has a negligible effect on the training in all configurations we experimented with. Finally, locality-sensitive hashing in attention is more major change that can influence the training dynamics depending on the number of concurrent hashes used. We studied this parameter and find a value which is both efficient to use and yields results very close to the full intention. We experiment on syntactic tasks, the text tags and Wiki8 with sequences of length 64K and image generation tasks, ImageNet64 with sequences of length 12K. In both cases, we show that the reformer matches the results obtained with full transformer but runs much faster, especially on the text tasks, with orders of magnitude better efficiency. Locality-sensitive hashing attention, dot product attention. So the dot product attention, I will skip bits of text here. It's a softmax of Q times Q matrix, query matrix, key matrix transform divided by a squared square root of dk end of the softmax times value matrix. Multi-head attention. In transformer, instead of performing single attention function, one linearly projects the queries, keys, and values h times with different learned linear projections respectively. Attention is applied to each of these projected versions of queries, keys, and values in parallel, yielding d-dimensional output values. These are concatenated, once again projected, resulting in the final values. This mechanism is known as multi-head attention. Memory-efficient attention. To calculate memory use of the attention mechanism, let us focus on attention computation from equation 1. And let's assume that Q, K, and V all have the shape, batch size, length, and D model. Main issue is the term Q times key transform, which is the shape of batch size, length, and length. In the experimental section, we train on models of sequences of length 64K. In this case, even at the batch size of 1, this is 64K times 64K matrix, which is 32-bit floats, would take 16 gigabytes of memory. This is impractical and has hindered the use of transformers for long sequences. But it's important to know that QK matrix does not need to be fully materialized in the memory. The attention can indeed be computed for each query separately, only calculating the softmax once in memory, and then recomputing it backwards on the backward pass when needed for the gradients. This way, the computing attention may be less efficient, but it only uses memory proportional to the length. We use this memory-efficient implementation of attention to run the full attention baseline present in the experimental section. Where the QKV come from, multi-head attention describes raw operational keys, queries, and values, but usually we are only given the single tensor of activation of A of shape, byte size, length model, D model, coming from emitting tokens in the sentence in vectors. Okay, I'm going to skip a bit of text here. Hashing attention for LSH attention, we start with two tensors, Q equals K and V of the shape of the byte size. Keep multi-head mechanism intact and focus on attention computation of equation 1. So they mentioned when issues QK, but know that we are actually only interested in softmax. QK, since softmax is dominated by largest elements, each query we only need to focus on the keys that are close to the QI. That is more efficient. Locality-sensitive hashing. The problem of finding nearest neighbors quickly in the high-dimensional space can be solved by locality-sensitive hashing. Hashing scheme that assigns each vector to a hash is called locality-sensitive if nearby vectors get the same hash with the high probability and distant ones do not. In our case, we actually only require nearby vectors get the same hash with high probability, and that hash packets are of familiar size with high probability. We achieve this by employing random projections as follows. See figure 1. We first fix on the metric, we define argmax as concatenation to this method is known LHA attention. Okay. I'm gonna skip this section. Figure 2, simplify depiction of LSH attention, showing the hash bucketing, sorting, and chunking steps, and the resulting causal attentions. Attention matrices for these varieties of attention. Analysis on a synthetic task. I'll skip this one. Session 3. Chunking. Related work. Experiments. Let's go back to the section Reversible Transformer. As the above section shows, the complexity of attention can be reduced from square in length to the linear, provided the approximation is acceptable. But it is clear from table 1 that each field starts with Bn term cost the activations. This section we show how to reduce this cost by first dealing with an part of the term used reversible layers, and then showing how chunking can allow us to handle the FF problem. RevNet. Reversible residual networks were introduced in 2017, where it was shown that they can replay ResNets for image classification. The main idea is to allow the activation at any given layer to be recovered from the activations at following layer using the only model parameters. Rather than having to checkpoint intermediate values for use in the backward pass, layers can be reversed one by one as the backpropagation proceeds from the output of the network to its input, whereas normal residual layer performs a function from X to Y that operates on a single input and produces a single output, and in the form of y equals x plus f function of x. A reversible layers works on pairs of input outputs, takes x1, x2, produces y1, y2, and follows equations. y1 equals x1 plus f function of x2. y2 equals x2 plus g as a function of y1. A layer can be reversed by subtracting rather than adding the residuals. So the x1 then equals y2 minus gy1. And x1 is y1 minus fx2. A reversible transformer. We apply the RevNet idea to the transformer by combining attention and feed-forward layers inside the RevNet block. In the notation above, F becomes an attention layer while G becomes feed-forward layer. Chunking. While reversibility recovers another term, the thicker layers can still use also memory. Feed-forward layers, particularly, can use intermediate values of dimensionality 4K or higher. Moreover, computations feed-forward layers are completely independent across positions in sequence. These layers typically batched by performing operations for all positions in parallel, but operating on one chunk at a time can reduce memory. Related work. Skip this one. Experiments. Figure 3. Effect of shared query key space left and reversibility right on performance on ENVIG8 and ImageNet 64 training. The curves show bits per dimension on held out data. So the bits, from all the 4 images, we can see that the bits per dimension on held out data are going rapidly down and then stagnate around some constant, converge to some constant value. Conclusions. The reformer combines the modeling capacity of a transformer with an architecture that can be executed efficiently on long sequences with small memory, even for models with large number of layers. We believe that this will help large, richly parameterized transformer models become more widespread and accessible. Also, the ability to handle long sequences opens the way for use of the reformer on many generative tasks. In addition to generating very long coherent text, the reformer can bring the power of transformer models to other domains like time series forecasting, music, and image generation. Okay, thank you very much for listening. This is the end of the reading of the reformer paper, and maybe see you next time.